In this video, I'm going to show you how to find the area bounded by a parametric curve and the x-axis in the case where the argument of the area integral changes sign. We want to find the total unsigned area traced out by this parametric curve. X is t squared, y is 4t squared plus t plus 5, where t ranges between -1 and 1. This curve just looks like a swoop. At t equals -1, we're starting with x is 1 and y is a little bit bigger than 5. Then, as t increases to 0, we're swooping down to hit the y-axis at 5. Then t increases to 1, and we're swooping up to finish off a little bit higher than where we started. There are really two areas here. There's the area below the bottom swoop, that's area 1, as t ranges from -1 to 0, indicated in red. And there's also area 2, which is below the top swoop, and that's in blue, that's as t ranges from 0 to 1. We want to find the total unsigned area traced out by the function, so that means we want to find the sum of both of these areas. Let's start off by getting an estimate for the areas. Each area contains a rectangle of dimensions 1 and 5, so each area should be a little bit bigger than 5. So then the total area, when we add them together, we should find that the total area is a little larger than 10. We'll just use this estimate to make sure our result makes sense when we compute it. Now, this problem is a little bit tricky because our usual approach of doing the single integral is going to yield a kind of weird result. And we're going to have to do something else to remedy that problem. But for right now, let's continue computing our single integral as we usually do and just see what happens. So the bounds here are t ranges from -1 to 1, so the integral becomes the integral from -1 to 1. And y of t, we're just given that in the function statement here, so we can substitute that in. 4t squared plus t plus 5. dx dt we can find using the statement of what x is here. X is t squared, so dx dt, we just differentiate with respect to t to get 2t. So we'll substitute in 2t dt. And now we can go ahead and compute this integral because now it's all in terms of t, and we'll do so. So that's the integral from -1 to 1. We'll distribute that 2t to get 8t cubed plus 2t squared plus 10t dt. And now we can go ahead and compute this integral. We'll integrate each of these terms, so 8t to the third. Well, that t to the third is going to become a t to the fourth, and then we have to divide by 4. So 8 divided by 4 is 2. Then for the next term, t squared will become t third, and then divide by 3, 2 thirds. And then for the last term, t to the first power will become t to the second power, and we have to divide by 2, so 5. And we want to evaluate that expression at the bounds 1 and -1 and subtract. So at 1, t fourth, t third, t squared, 1 raised to any power is just 1, so we're just adding up all the coefficients. 2 plus 2 thirds plus 5. And then we have to subtract when we plug in -1. -1 to the fourth is just 1, so the first term is just 2. -1 to the third power is -1, so now we have -2 thirds. And -1 squared is just 1, so the next term is 5. And to do this computation, we'll distribute that negative sign, so 2 plus 2 thirds plus 5 minus 2 plus 2 thirds minus 5. And a lot of things cancel. There's the 2 and the minus 2, there's the 5 and the minus 5, those all cancel, and we're just left with 2 thirds plus 2 thirds, which is 4 thirds. But hold on a second. The estimate was that our area is a little larger than 10, and 4 thirds is way smaller than 10, so that can't be right. What's going on? It turns out that this result is actually the difference of areas. This is just the top area, area 2, minus the bottom area, area 1. And the reason why this happens is because of this expression inside of the integral. This expression changes sign when t is 0, and that's within the region of integration. which ends up causing one of the areas to have a different sign from the other. When we try to perform our computation with just a single integral, we end up ignoring the signs of the areas, and it turns out that one area is subtracted from the other. So it makes sense that we should get a result that's just the difference of areas. But how do we get around this problem and compute the sum of areas instead of the difference of areas? Well, the answer is just to compute each area separately. We need to break up the problem into two integrals, one for area 1 and one for area 2. So we'll do that here. Area 1 will just be that same integral, but over the bounds -1 to 0. And so since this is the same integral, we can just use a lot of the work that we've already done. So we can get to this point here. So that's just the quantity 2t to the 4th plus 2/3 t squared plus 5t squared. Oh, this should be to the 3rd. Between -1 and 0 this time instead of 1. So let's go ahead and do that computation. So that is just plug in 0 and, well, all of the terms go to 0. So you just get 0 minus whatever happens when you plug in -1. But we already plugged in -1. That was over here. So we can just use that information. So 0 minus 2 minus 2/3 plus 5. And so that is just 0, well, we'll forget about the 0. And this is just minus 2 plus 5 is 7, minus 2/3 is 6 1/3. So area 1, this integral comes out to -6 1/3. But we want positive area, not negative area, because we want the total unsigned area. So we actually have that area 1 is just equal to +6 1/3. Okay, now let's do the same thing to find area 2. So area 2 is the integral from 0 to 1. And we've already done the integral computation, so we're just going to proceed like we did before. That's 2t to the 4th plus 2/3 t cubed plus 5t squared. Evaluated at lower bound is 0 this time, top bound is 1. So this is just everything evaluated at 1. We already did that over here. So that's just 2 plus 2/3 plus 5 minus everything evaluated at 0. And all that evaluated at 0, every term goes to 0, so just 0. So now we just add up everything and we get that area 2 equals 7 2/3, which is positive, so that's it. That's area 2. Alright, so now the total area, let's put A total, is just the sum of the areas. That's equal to area 1 plus area 2. And area 1 is 6 1/3. And so we have to add area 2 to that, 7 2/3. And when we add that, we get 6 plus 7 is 13, 1/3 plus 2/3 is 3/3, which is 1, so just 14. So that is the total area. And that makes sense with our estimation. It's a little bit larger than 10. We can also check to make sure this answer made sense from our single integral. That should be the difference of areas. So if we take the difference, 7 2/3, and subtract that 6 1/3, then that's just 7 minus 6 is 1. 2/3 minus 1/3 is 1/3, which is just the same as 4/3. So it makes sense why our single integral gave us the answer that it did. So the takeaway of this problem is that if you want to find the total unsigned area, you need to make sure that the argument of your integral doesn't change sign. If it does, like here, then you have to split it up wherever it changes sign, because some areas will come out negative and you'll need to change them to be positive before you add. And that'll get you to the actual correct answer for the total area. In the future, we'll also learn how to perform other computations with parametric curves, such as finding arc length.